But I think today is an auspicious day too, as you will see. So let me get started. So as the title says, it's from paradox to reality. And as you know, this year's Nobel has gone to these three people, Alain Aspect, John Clauser, and Anton Zeilinger. The Nobel Prize in Physics 2022 was awarded jointly to them for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. Actually, the story, though, starts long ago, nearly 90 years ago, in 1935, when Schrödinger, along really with the development of quantum mechanics, there were these amazing people who were developing the theory as well as thinking about it really deeply. And so clearly, all of them were involved in the clarification of this aspect, and central to this entangled photons is the word entanglement, which was first described by Schrödinger as when two systems enter into temporary physical interaction, and after a time of mutual influence, the systems separate again, they can no longer be described in the same way as before. I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. By interaction, the two representatives, the quantum states, have become entangled. So what is so peculiar about entangled states was also appreciated by Schrödinger, and he, in his words, the best possible knowledge of a whole does not necessarily include the best possible knowledge of all its parts. So think about it. If we know the state of a joint system, obviously we think we know the states of the constituents. If we know everyone in this room, we know the name of every one of them. But that's not the case with a quantum state, where you may know the entire quantum state, but if you ask for the state of a single constituent of that, you may have absolutely no knowledge about it, even though they may be entirely separate. And this is a rather interesting and very prescient observation. It is rather discomforting that the theory should allow a system to be steered or piloted into one or the other type of state at the experimenter's mercy, in spite of his having no access to it. So this is what created all that controversy and interest around entangled state. The fact, as we will see repeatedly, the fact that we seem to be steering some states which are very non-local or far away from where it's being steered. So it is into one or the other at an experimenter's mercy, in spite of his having no access to it. So this seems to be very strange. So just to give you already, I won't be using a whole lot of math. In fact, the subject need not be math intensive, but it is really conceptually quite subtle. And I should also say that I'm not a foundations person as such in my research aspects. So it's something which actually requires dwelling into as almost an entire career. So here I'm just showing a coin in which there are actually two coins which can be in head or tail. And as you know, there are four possible configurations, obviously. These are the four possible configurations out here. So this is a classical state of these two coins, if you wish. And these are the states of the first coin, second coin, and so on. And when any of these coins are in, let's say, this particular state, HT, if we were asked what is the state of the first coin, you would say H, second coin is T. So that's rather obvious. So here is a case where we know the state of the entire system, and we also know the states of the parts of the system. We know the first coin is in head, the second coin is in tail. However, quantum mechanics allows for superpositions of such states. And therefore, there is this superposition, this simple superposition of this HH plus TT is a genuine state of these two coins. This kind of a superposition if we were to ask what is the state of the first coin, it's clear that we cannot ascribe a definite state to it. It's neither head nor tail. So this is an example of an entangled state, and from this flows all of this, a whole lot of interesting consequences in physics. So after Schrödinger pointed this out, or maybe around the same time actually, there was this seminal work of Einstein, Podolsky, and Rosen, which I will mention in the next slide. But this is the world according to Einstein. And it's not just the world according to Einstein, it kind of enshrines some basic principles of causality and realism, which we take for granted, but we will spell it out. We'll spell it out so that it's in black and white. So Einstein used these two words, local and realistic, for the physical world. Just to put it simply, local means that there can be no faster than light communication. So you can't have action at a distance, for example. So this is an assumption behind, I mean, this is something which the physical world, the phenomena in the physical world are supposed to obey. Action at a distance was never there in favor, but then light was, as you know, is the fastest speed of communication, and therefore there cannot be anything greater than the speed of light. So this is called locality or local. Realistic is a slightly loaded word again, so it almost reads like philosophy at this point. But realistic means that measurements can only reveal pre-existing elements of reality. So in this paper, which I will show in the next slide, there is a clear statement of what they think is realistic. It means that if you have a system and you're not disturbing it, without disturbing it, if you're able to ascribe some value for a variable, then that variable or that quantity is an element of reality for that system. So this seems, for example, just at a gross level, I see a duster there, it looks green to me. So there's an element of reality. Of course, I'm observing it, but that observation has not changed this fact. So I will say that I'm ascribing some element of reality to it, which is the color green. And when you measure something, you're only revealing what already exists as an element of reality. So this is again something which we assume. We assume that suppose there's a particle which is traveling at some speed, and you're measuring the speed, and you get 5 meters per second, you assume that before your measurement, the particle was traveling at 5 meters per second. That's it. I mean, that's your observation is simply revealing what was already there. So this is realism. That is, observations are revealing what was there. So now we come to the paradox part of the title, that quantum non-locality is that these three gentlemen here, Einstein, Boris Podolsky, and Nathan Rosen, wrote this paper in 1935. So let me read out and the title was, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? In a complete theory, there's an element corresponding to each element of reality. A sufficient condition for the reality of a physical quantity is a possibility of predicting it with certainty without disturbing the system. In quantum mechanics, in the case of two physical quantities described by non-commuting operators, the knowledge of one precludes the knowledge of the other. Like we study in our courses, that position and momentum is the first things which we study, that you cannot measure them with accuracy at the same time. They don't commute, and therefore starts all quantum mechanics 101. So that's an example of this. So they go on to say that the knowledge of this precludes the knowledge of the other. Then either, and here they they introduced these two things. And either one, the description of the reality given by the wave function, as you know, the wave function is a basic object in quantum mechanics. The description of reality given by the wave function in quantum mechanics is not complete. Or two, these are the two possibilities, and these are mutually exclusive. These two quantities cannot have simultaneous reality. Because if they have simultaneous reality, then you can actually ascribe a value to each of them. Consideration of the problem, and this is what they're talking about, what they are doing in the paper, consideration of the problem of making predictions concerning a system on the basis of measurements made on another system. So there are two systems, and one is making measurements on one system and concluding the variables or concluding something about the other system that it has previously interacted with it, leads to the result that if one is false, that is, if quantum mechanics is true, then two is also false. That is that you can have, if quantum mechanics is true, let's put it simply here, quantum mechanics is true, it is possible for non-commuting observables to have simultaneous values. It is possible to ascribe reality to non-commuting variables if quantum mechanics is true. That's essentially what this abstract says. One is thus led to conclude that the description of reality as given by a wave function is not complete. This paper has an background, an interesting background, or I believe Einstein later said that this paper was almost exclusively written by Boris Podolsky. So in terms of the words and the emphasis was by Boris Podolsky. And before it appeared in print, it appeared in New York Times as Einstein finds the quantum theory to be incomplete. And it was in Einstein and two other colleagues of his. I believe an interview was given by Podolsky, and then Einstein sent a letter to Times saying that he does not operate like this. He would first have scientific discoveries in the proper, or scientific debate in proper media before going to the other media. And then actually this led to some amount of shift of emphasis from what Einstein himself wanted to look at or wanted to emphasize. But the same year, very shortly after, this paper was in March. The paper appeared in July with the same title in the same journal by Niels Bohr, as you know, the founder of quantum mechanics, what's called now the old quantum theory. It is shown that a certain criterion of physical reality formulated in a recent article with the above title contains an essential ambiguity when it's applied to quantum phenomena. In this connection, a viewpoint termed complementarity is explained, from which quantum mechanical description of physical phenomena would seem to fulfill within its scope all rational demands of completeness. So as you know, the viewpoint which was emphasized by Bohr is called the Copenhagen interpretation, and Bohr repeatedly harps on complementarity, which is simply saying that you have two conjugate variables like position and momentum. You should not talk about, not only can you not talk about measuring it simultaneously, you should also not talk about them as in a way which is, if you had measured the position, you would have got 5 meters. And if you had measured the momentum, you would have got 10 meters per second. These two kind of statements are not correct. So I'll tell you in a minute what I mean by that. And realism is ambiguous. It is a very act of measuring one or the other conjugate variables that makes them exist. So this seems a little bit mystical, but this is actually the viewpoint of mainstream quantum mechanics, that if you have conjugate variables, it's not, and you measure them, what you are measuring you cannot ascribe as a value which pre-existed before the measurement. So if you found a value of position to be whatever you find, it does not mean that that you can ascribe that a state with that value of position to it. So what was it which was there in Einstein's paper or EPR paper which led to this discomfort is in fact an entangled state. It was an entangled state where you're imagining two particles which are, let's say, in some kind of decay. They are going away from each other in opposite directions, and if you measure the position of one particle, which is very far away, let's say that they are separated very far away, you measure one particle's position, you can infer the position of the other particle, because x1 minus x2 is a constant, or is equal to some constant. So you can always measure what is this, or if it's just flying apart from a 0, then if it's minus x1, the other one is plus x1. So you can infer the position of that. On the other hand, so that means you have not done any measurement on one of the particles, but you have found its position. And therefore you would say that the position had some reality to it, was an element of had an element of reality. It satisfies the definition. If you, at the same time, you could also measure the momentum of the particle instead of position, and you would find the momentum of the other particle as well, because they are just flying apart with equal and opposite momentum, right? So without, again, disturbing one of these particles, one pair of particles, you can find out its momentum. And therefore these values of position and momentum should have existed as elements of reality. However, they are complementary variables. I mean, they cannot be measured at the same time, according to quantum mechanics. So this is essentially the paradox which was put forward by EPR, and saying therefore that quantum mechanics cannot be complete. This started also a chain of work. I'm not going to go into the historical details of that. A very interesting chain of work starting with de Broglie and in fact Bohm. But Bohm introduced a much simpler model than what we call continuous variables these days, with just considering, let's say, a spin 0 particle which decays into two spin half particles. So now what happens is you just go to the simplest quantum system where you only have two levels, a spin half particle. So here you have a source. Particles which are these two spin half particles are in a spin singlet state where the total spin along any direction is 0. And this singlet state is just written as in any basis or in any particular direction. Let's say you take the z direction, so that's the spin along the z direction up into the spin of the other one being down minus the reverse order. But the same state can also be written as what I've written below when in terms of x or any other direction for that matter. Now, if you choose to measure, let's say Alice, so Alice gets one of these spin-off particles, Bob gets the other particle, and Alice chooses to measure in the z basis her particle. What it means, you've all studied the Stern-Gallac experiment, which is, and you know that the result of this Stern-Gallac is just a plus minus 1 or plus minus h bar by 2, which is telling you the spin components. Thank you so much. Right. So if Alice chooses to measure her spin in the z direction, she would get either this up or minus with equal probability. This is what the laws of quantum mechanics tell you. Let's say that she gets this state, Z plus, her counter clicks plus 1, then she knows for sure that Bob's spin is in Z minus. See? So this is what Schrodinger in effect calls steering, because Bob has done nothing. He has a spin half particle. Alice has her spin half particle, and she makes a measurement on it, putting a Stern-Gerlach field in the Z direction, and she finds that the plus 1 has clicked. And now instantaneously she knows that Bob's state, if he measures it in the Z direction, is minus. He will get a result minus 1. And of course, this is the other possibility. This itself may not be that discomforting. What is discomforting is that she can choose to not measure Z, but can measure X component, in which case she will get one of these two, again with probability 1/2. So if again her plus 1 clicks, her state is going to be X plus, and the state of Bob's is going to be X minus, which is extremely different state than Z minus. So this is looking like it's violating several things, especially it's violating locality, because it seems like Bob's state can be instantaneously changed from Z plus, or it can be instantaneously put into any one of these kind of states, can be steered into any one of these kind of states depending on Alice's action. And they can be separated by a very large distance so that they are space-like separated. No light signal can reach between, can reach them. So this seems to violate locality. And this is essentially what Einstein was also complaining about. And this is really what was his concern, rather than whether you're able to predict X and Y, X and P simultaneously or not. But the same thing here. You know that not all the components of spin can be measured. They are actually, again, complementary variables. You can't measure, you can't find the values or ascribe a value for, let's say, X, Y, and Z components of this particle simultaneously, like plus 1, minus 1, minus 1. You cannot do that. But again, at this point, what would you say? If suppose Alice has made a measurement of X and has got a plus 1 click, you're saying that you have, so Bob now has a state which is minus instantaneously. So this simplification of Bohm in this way led to several important insights, and this was the paper which kind of started it all. Really taking these considerations from what sounds like philosophy or at best metaphysics into the laboratory. So this was the work of John S. Bell. I believe this is a journal which was very short-lived, no longer exists, on the Einstein-Podolsky-Rosen paradox, 1964. The paradox of APR was advanced as an argument that quantum mechanics could not be a complete theory. These additional variables were to restore to the theory causality and locality. So these additional variables, this incompleteness, is come to be known as hidden variables. In this note, the idea will be formulated mathematically and shown to be incompatible with the statistical predictions of quantum mechanics. That is, that the notion that you can supplement quantum mechanics by additional variables and make it complete. John Bell showed in '64 that this leads to results that are incompatible with the statistical predictions of quantum mechanics. It is a requirement of locality, or more precisely that the result of a measurement on one system be unaffected by operations on a distant system with which it has interacted in the past, that creates the essential difficulty. There have been attempts to show that even without such a separability or locality requirement, no hidden variable interpretation of quantum mechanics is possible. These attempts have been examined elsewhere by John Bell and found wanting. Moreover, a hidden variable interpretation of elementary quantum theory has been explicitly constructed. He is actually referring to Bohm's theory, which is now known as Bohmian mechanics, which is a very successful theory which has hidden variables in it, which actually changes, which introduces something called a quantum potential, but is actually manifestly a highly non-local theory as well. That particular interpretation has been grossly non-local, that's what he's saying. This is characteristic, according to the result proved here, of any such theory which replaces, which reproduces exactly the quantum mechanical predictions. So what John Bell showed was that it's possible to take these ideas and to see which one is correct, whether in fact locality is being violated or not in quantum mechanics. So, but he shows something very interesting in this paper, and I encourage those of you who have not read it to read it. It's completely accessible. He shows first that for a single spin-half particle, nothing simpler in quantum mechanics than that, say in a state Z plus, as we have discussed, a hidden variable theory is indeed possible. So, for instance, suppose you're measuring the spin along the direction A, and the state is Z plus, then the expectation value is cos theta, where theta is the angle between A, that this vector A makes with the Z axis. That's quantum mechanics. However, you can ascribe a purely classical function, let's say A, which depends, capital A, an observable, which depends on the direction of the spin particle, and these are the hidden variables, lambda, all clubbed together. They can be any number of variables, it doesn't matter. It's just generically called lambda. It takes only two values plus minus 1. Okay, I have not written here explicitly the model. You can look at the paper. But there is an explicit way in which, given this direction A and the value lambda, you can find this to be plus minus 1. But this is a hidden variable. We don't have access to it, but we know some statistics about it. So that statistics is embedded in this function rho of lambda. So this is the probability density of finding this hidden variable lambda. And this average is then calculated, and what Bell showed was that it's possible to find a rho of lambda such that you get this to be cos theta, which is the quantum mechanical result. So quantum mechanics can appear to be, you have some averages which you're getting out of quantum mechanics. You can think about these averages as some kind of classical averages of some underlying statistical theory. And if you knew the lambda value exactly, then you would be able to find exactly whether the spin was plus 1 or minus 1. You don't need to look at a probability. However, he also showed in the same paper that this is not possible if you have two spin-half particles. Especially if you have two spin-half particles in the spin singlet state, which I showed you before, this is certainly not possible. And he showed this by looking at these kind of correlations between spin measurements of these two spin-half particles. So now you have two spin-half particles, so you can make measurements on each one of them independently, and along two directions, let's say A and B. Then this is a quantum average or expectation value, just as this one is cos theta. You can evaluate what that is. It's just minus A dot B when the state is a singlet state. What he showed was that it's not possible. Suppose there was actually some hidden variables, and this is the observable which you get on spin 1 or spin A along, this is the one with Alice, let's say, and this is the spin with Bob. Then you calculate this hidden variable average. It's not possible to reproduce the quantum average, whatever may be the value of rho of lambda, whatever may be this function rho of lambda. There are some important things in this thing. The fact that we have factored this, that we have factored this thing here is an assumption of locality. That the probability is just this. I mean, first of all, the result of the measurements on A do not depend on the settings in B. So this is just a function of A. Okay, so this is the locality condition here, and also this probability density does not depend on the settings A and B. That is, this hidden variable should not depend on what observables you're choosing to measure. So this is actually he formulated an inequality. I will come to that, which showed that this equality is not possible. And therefore, most importantly, if you have a spin singlet, which is an entangled state, it's not possible to have any kind of local hidden variable theory which will reproduce quantum results. So I found it rather peculiar when I saw this, that by some strange correlation, if you look at the date of this paper, it's 4th November. So it's kind of, that's why we arranged it today, as you know. Today is John Bell Day. So John Bell, for those of you who don't know, was a particle physicist working at CERN. And as he put it, he did quantum mechanics on Sundays. This is from the website of the Royal Irish Academy. On 4th November 1964, that's 58 years ago, John Bell from Tate's Avenue, Belfast, changed the world of science by laying the foundation stone for quantum computing and his quantum theory. So this is celebrated today. Today is John Bell Day, so it's great to talk about this. I believe in 1990, unfortunately he died rather early, he was nominated for the Nobel Prize and would have most likely got it. So indeed, this year's Nobel Prize owes a lot to the legacy of John Bell himself. So from Bell, we come to, he influenced this whole lot of work after that, and the first Nobel laureate of this year, John Clauser, John Clauser's work, so this is actually along with Hone, Shimoni, and Holt, they proposed an experiment as well as as another quantity to measure, which has supplanted Bell's inequality to a large extent, being very simple to see and apparently also to measure. In fact, all the experiments measure what is called the CHSH inequality or CHSH quantity and see whether there's any violation of that. They proposed this experiment. This is in 1969. There is a nice review of this in Reports of Progress in Physics in 1978 by Clauser and Shimoni. And this is actually the experimental setting of all of these experiments, where you have a source of entangled particles which are producing these singlets. So one of them is going to Alice and the other is going to Bob, and Alice can measure this according to different settings. So she can turn, you can imagine that Alice has a Stern-Gerlach or some kind of polarizers, as we will come to in reality, and she can turn these Stern-Gerlach apparatus or polarizers according to her wish. So she would have these in multiple settings and measure plus minus ones. So the detector always detects either +1 or -1, and if there is no detection, it's a dark count, she has nothing, 0. And similarly, Bob. Okay, and then, so what they have at the end of the day is a series of measurement results with Alice, which is a series of plus minus ones, and a series of plus minus ones for Bob. out of this plus minus ones, we have to deduce whether locality is violated or not. How do you do that? So this was the all inspired by John Bell. So let Alice and Bob get one particle each on which they perform two possible measurements. By the way, you can forget about quantum mechanics for the time being and just think about it as two particles. You're making two possible measurements on each of them, and the outcome of the measurements are just plus minus 1. It's binary outcome. Okay? Two possible measurements on each side and two possible outcomes, plus minus 1. And this is what classical or hidden variable theory will give you for a quantity such as this, where this A1 is a result of Alice's measurement 1. So Alice makes two measurements, A1 and A2. Bob makes two measurements, B1 and B2. Can make two measurements. It's not as if they're making two measurements on the same particle. They are making either a measurement B1 or B2. Alice is making either a measurement A1 or A2. Okay? And now, each one of them is plus minus 1. You construct this quantity. I have just written it down already with brackets. A1 B1 minus A1 B2 plus A2 B1 plus A2 B2. So all possible combinations of these things, but one of them has a minus sign. Any one of them, by the way, can have a minus sign in this quantity. And let's just look at this, and a very simple naive analysis will tell you the following. The results of B1 and B2 can be either plus 1 or minus 1. Let's say that they are the same. Let's say plus 1 plus 1. Okay? If they are the same, then clearly the first term is 0, and the second term can be at most 2 or minus 2. Can be either 2 or minus 2, because B1 plus B2 adds to 2 or minus 2, and A2 can be plus or minus 1. Okay, so this entire quantity can be either plus 2 or minus 2, and similarly they can be different, in which case the second term vanishes and this will be plus minus 2. So this entire CHS-SH quantity can be either plus 2 or minus 2. Now, what you do is you look at a run of many times. You have many of these particles, and then you take the average of this quantity. The average of this quantity is going to be less than 2, because each one of these things is either plus 2 or minus 2. Okay, so the average of it is less than, so the average modulus is going to be less than or equal to 2. So this is an example of a Bell inequality. There are actually millions, there are a lot of Bell inequalities these days. So this is the inequality which was studied by CHSH in their paper. And there is some subtleties behind this, but essentially the argument is very similar to what was shown by Bell, that whatever you may have as some hidden variable distributions behind it, this is always true. It can never be larger than 2. But note that there are some strange things here. When I say that B1 minus B2 can be either plus 1 or minus 1, I'm now talking about really two observations which are never done, because you're either doing B1 or you're doing B2. Similarly, you're either doing A1 or A2. So even when we are saying that, we are assuming that there are really properties B1 and B2 with that particle. This is realism. We are assuming that there is really something there. Suppose I measure B1, I'm going to get 1. I'm going to say that actually B1 value was 1 before I measured it. Okay, so that's why this kind of argument actually takes into account both realism, it assumes behind the simple math, realism and locality. What about quantum mechanics? In quantum mechanics, again, you can have two possible settings of your Stern-Galerk apparatus. Let's say along the directions AI, small ai is the A1 and A2 for Alice, and B1 and B2 for Bob. And then these are the observables, as we know from quantum mechanics. And you can put the singlet state, and actually you can you can take the singlet state and find this expression's average. This is quantum mechanics. It's a nice exercise in quantum mechanics. You will find that it's equal to twice root 2. Average of that is twice root 2. And it was shown that this cannot exceed twice root 2. This is the maximum possible value. But this is already 2.8, whereas this is only 2. So quantum mechanics allows for this quantity to go as high as 2.8, whereas classical or hidden variable theories allow for it to go only up to 2. And therefore, if you make some measurement of this quantity in a laboratory and find anything greater than 2, this is evidence that is that there is a violation of locality, realism, or both. So in fact, the optimal violation of this 2 is, for example, in the case where these measurement directions A prime, so this is A1 and A2, this particular diagram is taken from this paper of this paper here. So they call it A prime and B prime instead of A1, A2 and B1, B2. But this is 45 degrees here. This is the ideal setting for this. You can think about these observables as X and Z in A direction for Alice, and for Bob, these other measurements. So this was, entangled photons were actually used by not spin half particles as such, but polarization degree of freedom of photons was used, and they were calcium atom. So this was early days, and they were looking at producing entangled photons from atomic transitions. And that's how Clauser did his work, as well as Alain Aspect. So this is the second Nobel laureate this year. The Nobel Prize went to him. Clauser set the stage, and there were some experiments which already, as a series of experiments, which showed that there was a violation. So people were quite confident that actually there is a violation of locality. And enter in the 80s the experiments of Alain Aspect and collaborators from France. Experimental realization of EPR, a new violation of Bell's inequalities. A linear polarization correlation pairs of photons emitted in a radiative cascade of calcium has been measured. New experimental scheme used 2-channel polarizers in a straightforward transposition of EPR Bohm-Gedanken experiment. The present results in excellent agreement with quantum mechanical predictions lead to the greatest violation of generalized Bell inequalities ever achieved. So they almost got to twice root 2 in these experiments, something like 2.6 or so. But there were, if you read the literature on this, it's extremely exacting in the sense that every possible loophole, it's actually called a loophole, is examined as a possibility. For instance, in these experiments of Alain Aspect, the settings, especially of Clauser also, I mean the settings of these A prime, B prime were fixed. For all the photons, everything was fixed. Now, there could be then some correlations because it is fixed, and there could be some kind of some unknown effect which is leading to these correlations. So if that is true and locality is, I mean, suppose there is communication between Alice and Bob, then Bell's inequality can be violated. Quantum mechanics is no longer is not the only thing which will violate that. So you don't want any kind of communication which is possible, and therefore there were these kind of loopholes which many of these early experiments suffered from, and they were being systematically plugged. Here is the same Alain Aspect very shortly afterwards, where he did experimental tests of Bell inequalities using time varying analyzers, where the attempt was that you want to you want to do the following. You have these analyzers here in Alice and Bob's side. You want to change, as this source emits two photons, before this photon reaches this analyzer, you want to change the mind of Bob and change the setting. Okay, so that there is no correlation between the direction of Bob, so that already, suppose this photon has some information that this analyzer is going to be in a particular direction. Maybe it's fixing the game. So that kind of thing is disallowed when you change this fast enough before the photon reaches here. Clearly a very non-trivial thing, and this was achieved by Alan Aspect in this by using time-varying analyzers. The switches operate at incommensurate frequencies near 50 megahertz. Analyzer in each leg of the apparatus is an acoustic optical switch followed by two linear polarizers. The results are in good agreement again with quantum mechanical predictions, but violate Bell's inequalities by 5 standard deviations. Again, they are looking at the CHSH quantity which I showed, so it is greater than 2. What does all these things tell us? If you stand back and look at it, it's telling you that if you haven't measured a quantity, it doesn't exist. Or rather, a quantity comes into existence when you measure it. And there is this very nice article by David Mermin, who wrote this in 1985, Physics Today. I encourage you to read it because it doesn't have any equations, but he actually derives Bell's inequality, a particular Bell's inequality. It's a beautiful paper. Is the moon there when nobody looks? Reality in the quantum theory. Einstein maintained that quantum metaphysics entails spooky actions at a distance. By the way, this is Einstein's words. Experiments have now shown that what bothered Einstein is not a debatable point, but the observed behavior in the real world. So it had become from paradox to reality. And he was talking about these experiments of Alan Aspect. The further refinements continued to be done. This is the work of one of the many works of Anton Zeilinger, violation of Bell inequality under strict Einstein locality conditions. So he wanted to really show that there cannot be, it's really space-like separated. The events in Alice and Bob are really space-like separated. So this is what was the attempt here in 1998. We observed strong violation of Bell's inequality in an EPR type experiment with independent observers. Our experiment definitely implements the ideas behind the well-known work by Aspect et al. We, for the first time, fully enforce the condition of locality, a central assumption in the derivation of Bell's theorem. The necessary space-like separation of the observations is achieved by sufficient physical distance between the measurement stations, by ultra-fast and random settings of the analyzers, and by completely independent data registration. You see, this is another thing. You have these two entangled photons going to these detectors. And then there is +1 and -1, let's say. How do you know that they're coming from the same event? They're coming from the same photons. So what's usually done was there was some, which means that there is some electronics which is actually connecting these Alice and Bob. So again, then a doubt will come whether there is some connection and there is some signaling happening between Alice and Bob. So actually what they wanted to do was to separate out the measurements. You have some time stamping, you should have clocks which are synchronized perfectly, atomic clocks which are synchronized perfectly, so that you know that independent measurements, you observe here +1, -1. And then at the end of the day, you compare everything and do your experiments. As well as ultra-fast and random settings. So they had a pure, what they call random number generator, a true random number generator, which means that's also quantum mechanical, okay, which will determine the settings of the Stern-Gallac or polarizers on both ends. And it was space-like separated. To achieve this condition, the observers Alice and Bob were spatially separated by 400 meters across the Innsbruck University Science Campus, which in turn means that the individual measurements as defined above had to be shorter than 1.3 microseconds, the time for direct communication at the speed of light. So they achieved this using, by the way, this distance between Alice and Bob was 400 meters. in the experiments of Alain Aspect, they were around 10 meters. Okay, so we had gone from 10 meters to 400 meters in the experiments of Anton Zeilinger, but this closed what's called the locality loophole, where you can be sure that actually they are separated by space-like separation. So this was, and they found, again, violations which were around 2 I forget now the numbers, but it was a large significance deviation from the many standard deviations from local realistic theories. So Bell tests were continued to be done. So here is one in 2015 appeared in Nature, where they did an experimental loophole-free violation of Bell's inequality using entangled electrons now. So this is not photons, separated by 1.3 kilometers. So it's a very interesting experiment again, where they use what's called entanglement swapping. So actually the entanglement is taken by photons, and then it's swapped by electrons to two electrons, which are separated by this large distance. And they found again the CHSH in Bell inequality 2.42, whereas that's 2 is the non-local, the local limit. So the limit the loophole which they fixed was what's called the detection loophole. When you're detecting photons, not all of them you will get. There are dark events. So I believe that in this experiment they are actually overcoming that entirely. So there has been increasingly detailed experiments which seem to show this. But this was also, I found that there was an interesting paper again in 2018 by a large number of people, and it's called the Big Bell test. Here one may argue that we use random number generators as quantum mechanical devices, but we are then using the theory itself to generate, how do we know that quantum mechanics is producing truly random numbers? So here is a sort of peculiar experiment where they use human beings as sources of random numbers. So let's see. Yeah. So they used, I think, 100,000 human participants. We recruited about 100,000 human participants to play online video game that incentivizes fast, sustained input of unpredictable selection and illustrates Bell test methodology. The participants generated 97 million binary choices, which were directed via some network and all that. And you see, there are so many stations internationally where they fed this data, and various inequalities were tested, CHSH and other inequalities, and these are the results of the violations here, the statistical significance, 57 sigma, and so on. So it's very remarkable. It tells us how random we are.
One short question. Why is the quantum mechanical calculation of the CHSH quantity an inequality? It should be a definite number.
It depends on the state. So the singlet. Huh?
You mean the inequality because you're running over averaging over different states?
No, the inequality as such, if suppose you had a singlet, you should get twice root 2.
Right.
Yeah. That's it. You mean why the experiment is not getting to twice root 2?
No, what are you assuming about A1 and A2 and B1 and B2? What statistics?
What are the settings? So they will take the optimal settings, like this kind of settings, where you'll get.
For a given setting, should it not be a definite number?
So it depends both on the settings and on the state. If you take a singlet and the setting, then it's twice root 2. Yeah, so this was proved by Serelson. It's called a bound that no other state can exceed twice root 2. So any setting, any state, it cannot exceed twice root 2. Yeah.
And would you know if, in the actual test, what's the statistics for which it's below the quantum and the Bell inequality in the CHSH quantity? What probability mass is there below 2?
In the experiments? Early experiments, it was very hard. There were so many, so many experimental factors which pushed it to be less than 2. I'm not sure I understand exactly.
No, I take that part. I guess if it exceeds 2, you automatically violate.
Yeah, you've automatically violated.
Even if 1.
So any pure bipartite state, there is some setting which will violate Bell's inequality. Okay, so anyway, I didn't show you how entangled photons are created at all. Now you don't need a calcium atom thing. Now there is this BBO crystals. You can go to Prem's lab, I suppose, or we actually have these kind of parametric down conversion. You can shoot a laser beam into it and get pairs of entangled photons. You can do these experiments these days. It's tabletop experiments. It should be done at the master's and PhD levels these days. And there are many uses of entanglement, but I think I've come to the end of the time. So actually, all of this till the 80s, even till the 80s, was more or less for foundations, locality, what is quantum mechanics telling us, and so on. But as the Nobel Prize itself says, that they laid the foundation to quantum information. That's because it went beyond the realm of foundations into applications or into using entanglement. So one of the major protocols which it was put to use was known as teleporting an unknown, is known as quantum teleportation. In 1993, these people described teleporting an unknown quantum state via an EPR Rosen channel. It just means using a spin singlet or a state and using the entanglement in that to teleport a state. This cartoon just describes that. So Alice has an LO photon, and then she shares with Bob a maximally entangled state, like the spin entangled state. She can do some local measurements and pass on 2 bits of information to Bob, so that lo and behold, Bob's photon becomes exactly what she had here. This LO photon goes to Bob. So this is known as quantum teleportation. Nothing happens physically. There is no teleportation there is no transportation of a photon, but nevertheless there is a transportation, an exact transportation of a state, an unknown state. Alice need not even know what the state is, but at the end of the day, Bob gets access to this. And teleportation has also been spectacularly demonstrated. So here is in increasing distances. This is now 1,400 kilometers satellite to ground teleportation of single photons, or teleportation of single photon states over distances of 1,400 kilometers by the group of Pan in China. Pan, by the way, was a PhD student of Zeilinger. So as you know, we have now gone from 2 qubits to many qubits. There are very beautiful experiments with 3 photon entangled states and so on, which I don't have time to describe. In fact, Zeilinger has a part of what's called a GHZ state. It is Greenberger-Hahn. Zeilinger state is a 3 photon entangled state where you can show non-locality without any inequalities. It's a beautiful experiment. You can read that up. And many qubits together, one is hoping to create a quantum computer. So we have right now access to something like 127 qubits in this institute, and you can actually play around with that. There is much more. If you go beyond two qubits, it becomes, or 2 particles like 2 photons or the singlet states. It's very interesting. You have all of these kind of applications, teleportation, secret sharing, dense coding, etc. Non-locality, which was like a philosophical thing, is used in device-independent quantum key distributions, randomness certifications, and so on. Once you have many qubits or these spin-half particles, obviously it's of interest in condensed matter systems, quantum phase transitions, many-body localization. We have many expert condensed matter people in the audience, quantum chaos, thermalization, atomic and nuclear physics. There's a lot of speculation these days that even the very structure of space-time is space-time itself emerges as some kind of entanglement, and don't ask me of what or between what, but there are all these words which again my colleagues know better than me. Tensor networks as models of quantum gravity. It's a very interesting time really. Black holes as information scramblers and so forth. So after nearly 90 years, entanglement is now being measured and understood as a fundamental property of space-time and matter, thanks to pioneers including John Bell, Clauser, Aspect, and Zeilinger. And there remains to be really much more to be explored and understood. I mean, it's not as if Bohr said the last word and we all now follow Bohr. It's not like that at all. We don't really understand, even if there is non-locality in some deep sense. So there are a lot of interesting problems, and you can get entangled and do the CHSH experiment yourself even today. You can log into this IBM site, create an account, and there is this thing called Qiskit. You can use that. Again, there are experts in the audience who know more about this, and you can do the experiment. Local reality and CHSH inequality. So thank you very much. That's all I have.
Fundamental characteristic of quantum mechanics, but it need not imply Bell non-locality. It need not even imply steering.
Scaling?
It doesn't even imply steering.
Steering. Why do you say that?
Locality would imply steering.
See, it depends now. If you stick to pure states, for example, of 2 qubits, then entanglement implies Bell inequality violations. So everything will, but it's not true for mixed states. You can have mixed states which are entangled but don't violate Bell inequality.
The state is entangled.
Yeah.
Don't tell you anymore.
Yeah.
You can't conclude that
No.
Bell non-locality.
No. Yeah. But we don't know. There are so many Bell inequalities. It may violate some Bell inequality which you don't know. So it may not violate this particular one, but you might find. Huh?
Entanglement,
Yeah.
if I understand right, doesn't necessarily imply Bell non-locality.
For a mixed state, yes, it doesn't include. Yeah. Jose, is that what? But only for a mixed state.
There's a bit. I only have one small question about this. Faster than light, within thousands of kilometers, over the microsecond distance. So how do the states change?
Wrote to the government in the US saying that there is this thing which you can use, non-locality, and do things much faster. But the fact is, of course, I mean, you'll find that in Mermin's article. But of course, you can't do anything useful with this thing, in the sense that, yes, Alice's measurement, so let's see here, so let's say that Alice has done the X measurement and she finds +1. She knows that Bob's is minus, but this doesn't make Bob any wiser. And this information for her to tell Bob that if you measure X, you will definitely get -1 requires classical communication. So as far as Bob is concerned, he is no wiser because Alice has done her measurement. So that's why actually the uses of entanglement, such as teleportation, is really something which is simple from some point of view, but is also magical at some level, because it's using this really to do something which cannot be done otherwise. But it does not violate faster than light communication. But still, it is a fact that, or if it is a fact given modern quantum theology, that indeed this state has instantaneously become this.
So the quantum superposition principle for the one particle state leads to the quantum entanglement event for the two particle state.
Say that again?
So the quantum superposition principle for the one particle state
Yes.
leads to the quantum entanglement for the two particle state.
Not necessary. Not all superposed states are entangled. But indeed, superposition is, responsible at the end of the day for that. but not just superposition. Yeah.
Sir, I have a question regarding the Fourier paradox.
Yeah.
Where you showed Bell's inequality.
Yeah.
As far as I understand, it depends on how you are defining the inner product between A and B. Can you go to the next slide where you are defining? Yeah. So how you are defining this A, B, rho, A lambda integral? The whole idea depends on this definition.
This one?
Yeah.
Yeah.
So my question is there a way to classify inner product cases?
No, there's no inner product or anything. It's just a product. There are two. These are just some scalars, plus minus 1. There's no vector here.
Yeah, but there is something special about this definition.
I'm just multiplying two numbers. What else can I do? I have plus 1, minus 1, multiplying it. That's all I'm doing. Integration is an average. So this need not be integration. For example, if your lambda has only 5 discrete values, it will be a sum over those 5 discrete values. It's just taking all of that into sum. It'll have some support on 5 delta functions. That's all. There's nothing deeper in this than that. Yeah. Yeah.
So in the starting slide you showed that Einstein said that there are two things,
Yeah.
locality and
Right.
realism.
Right.
So
Right.
all these CH, SH and Bell's inequalities, they prove that quantum mechanics is really non-local. So that argument is closed, but the realism argument is still there, right? So
No, it's not very clear. These are, again, at the end of it, they're words, and they are themselves entangled in the sense that, realism in fact is routinely violated. I mean, if you assume realism, what does it mean? Before you make a measurement, the value which you observed after measurement existed. Then it leads to, if you assume this, then it leads to contradictions.
So what we learn,
Even without inequalities.
yeah. So Copenhagen interpretation assumes realism is not true, and so that's how we've been. So that's how we got all our measurements, right? So that's how we know that. So quantum mechanics is, so it gives the right result. But there are also other theories. So hidden variable, so it can be discarded here. But other interpretations such as David's or cubism, those still argue about the realism fact, right? So that argument is not closed.
I'm not an expert. Now I have to confess that there are so many versions of quantum mechanical interpretations. I know only the canonical version of quantum mechanics. And some of this kind of things. There are a lot of interpretations, and there is some controversy. But I would say that experiment favors with I think very convincingly just the standard quantum mechanics, and whether the interpretation you want to believe in X, Y, or Z, that's up to you. But the fact is that if you think about measurements as revealing something which is pre-existing in whatever interpretation you may have, it's going to lead to problems with experiments.
Sir,
Yeah.
sir, isn't entanglement a logical consequence of superposition? I mean, it is inevitable. It's same to me.
It is a consequence of. So I mean, there was a question whether superposition and entanglement are related. Indeed, yeah. Here are two particle states. If you superpose them, typically they will be entangled, which means that you cannot say that here is a state for particle 1 and particle 2. Indeed. Yeah.
Are there any other questions?
By the way, I mean, entanglement is not some. It wasn't that entanglement was controversial. Let's first get that out of the way. Okay, I mean, atoms, as I said in my abstract, like atoms and molecules are entangled. I believe Clauser said that he was discouraged by Feynman to do these experiments because he said, well, you're just going to verify quantum mechanics. But the thing is, the beauty of this thing only comes when you are spatially separated, when you're well separated, and then you start seeing things about, the apparent action at a distance and so forth. Yeah. So entanglement as such is not a controversial thing. Although for a very small minority, even that is. Yeah. Yeah. Aditya.
So, you mentioned that the violation of this CHS search depends on the state and the measurement you make, right? So, doesn't that sort of give different types of entanglement because each state violates it?
So it gives you different measures of entanglement. So you can, you have a state. So in fact, the one which is giving you maximum violation, the spin singlet, is also maximally entangled. If you take a state which is less entangled, it will give you less violation.
Just use as a sort of metric.
You could, but it's not one-to-one. You have to be careful. But yes, it is related to that.
Good.
Oh, go ahead. I thought I had something written, but I didn't. Yeah.
What happens to this entangled system in presence of a part or
What happens to entangled system in?
presence of a part?
Bath. Yeah, so this is something that is, in fact, that's the big problem, right? I mean, entangled photons or entangled any particles, when they start interacting with other particles, there's something called monogamy of entanglement. So two maximally entangled particles cannot be maximally entangled with anything else. If A is maximally entangled with B, that's it. A cannot be maximally entangled with anything else. This is not a classical property. Classically, you can have three variables that are perfectly correlated with each other. But this is again a peculiar quantum property of entanglement, quantum entanglement. And therefore, if you have other bath, as you call it, they'll start getting entangled with that and start losing entanglement with each other. That's the central problem of, faced by when you're isolating quantum systems and you're trying to find quantum effects in them. In fact, thermalization is occurring because of entanglement with other degrees of freedom.
Sir,
Yeah.
so in proving these theories like this, not having an actual random number generator, is it a bottleneck?
Is it what?
Is it a bottleneck to not have a random number generator?
No, people have this quantum random number. They assume, because quantum theory tells you that when you make a measurement, you're getting with probability half, let's say +1 probability half, you're getting -1, that these are genuine random number process.
So when you're writing the expression for the CHS equality, you meant A1 and A2 need not be measured in the sense. A1 would be...
I mean, in any given run of the experiment, Alice is measuring either A1 or A2. So at any given time, she has only A1 value and A1 value, let's say, or A2 value, but not both. But when you're running, let's say, 1 million runs, then of course you'll have all possible combinations: A1, B1, A2, B2, etc. Therefore, you can make that. You can construct that quantity, and you're assuming their realism because you're saying that I have A1 minus A2. It makes sense to me because, or B1 minus B2, because there is a value of B1 which I'm measuring, but there's also a value of B2, but I'm not measuring it.
So in a given run, B2, when it is not measured, it is assigned a value of C.
No. You see, when you are, you just look at this, it's a product of only two of them at any given time. So A1, B1, A1, B2, etc. So you will find the average of these quantities. So I encourage you to read this beautiful article. Yeah?
Sir,
Yeah.
so in the experiments to see the violation of Bell's inequalities, we were seeing that we were using progressively longer distances to ensure space-like separation.
Right.
But even if you do the experiment in 10-meter separation or 1,000-kilometer separation, they're always space-like separated. Because
No, you have to, how is it always space-like separated?
because I have
See, you have some time at which, let's say that they are separated in that Zeilinger by about microseconds, right? So you have all your electronics and you have some time scale for that. That time scale, you should be sure that you have only one particle which is arriving here and there, not a whole lot of particles. You can't actually then distinguish one from the other, one pair from the other. If it's very short, you can't do that, right?
this sample is emitting particles continuously.
So I think it all depends on the detectors, how fast your detectors are going to respond and so on. There's a response time for the detectors. For a theorist, yeah, you can always do anything.
Okay, so I think it's time to close, but before we close, could I request Professor Balakrishnan to kindly present?
Bala is doing the honor now.
Yeah.
Thank you so much. Not my work.
I don't know what's in it. It could be a bell.
We need to, yeah, this is one of the boxes that Bob has. Thank you all very much for this, and it's a pleasure to not talk about my work.